I've allowed the mic. Let me share the PPT. I hope you are able to see the content. We were supposed to actually start session 4, but we have something left in session 3. So we would cover that and then we'll move on to session 4. We'll wait for 10:30. Everyone is supposed to join. Then what we can do is I can just let you go what we did in the previous session, right? Just go through what we have done. Can you all hear me? Anyone can respond?
Yes, sir. Please go ahead.
Yeah,
Yes.
yeah. Thank you. So if you remember, we started with regression, linear regression, right? Using a neural network approach. And if you remember this, we actually have started with an example so that everyone can get the entire thought process. Yeah. So if you remember, we took this particular problem with this being X and this being Y, if you remember, isn't it? Then I showed you the entire process that how a single neuron can be used. You know? Single neuron can be used for solving a simple linear regression problem with one variable, right? We have already done that, right? So this is just a kind of revision that I wanted to do because today we would be doing a little bit more and we have to come up to the session 4 as well. So as you can see, we assumed W and B, right? We assumed base fair as the bias value. So this is a simple equation that, if you remember, is nothing but a linear regression equation, right? So we model this equation in the form of a single neuron model. Then we started with the loss function, right? Isn't it? We talked about the gradients, right? We talked about how the gradient descent update has been done in this particular example. I hope you were there in the previous session. So this was covered in the previous session, right? Then I started with epoch 0, how the things is happening with the assumption of these weights, isn't it? I showed you the computations, right? We computed the error and then we were doing the square of this error, right? Then we computed the mean square error, right? And then this was after epoch 0. Then I showed you the updates, right? How the gradients got calculated, right? And then ultimately we came up with the sum of errors, right? And we plugged in the formulas. So I showed you the after result or epoch 0 what happened, right? This is what we got. And then we computed the MSE. So this is what we got. And then I gave you the next the entire iteration, what is happening with each and every input. If you if you can go through it, right? I hope you must have gone through it. Then we calculated the MSE again for the second, and this is what I was trying to show. Obviously, I cannot show the entire calculations for all the phases and all the iterations. And just to give an idea that what is happening, how is this MSE is decreasing, right? So there are phases when we can see that at this stage it started showing 0, right? And then at some stage over here, or maybe at some other stage, you can stop, right? That boundary has to be decided, right? Normally, a person might choose this boundary where the MSC has started showing zero. Otherwise, some other person might like to see that it becomes little consistent, and he is assured that he can stop over here also, right? So anyway, we suppose we take a decision that we stop over here, and that is what we actually get. And from where you can actually can plug in that particular formula of mx plus of b, you can put the values over there, that what we learned. So w becomes m over here, b becomes this. So ultimately you get a equation, and then on the basis of that equation, you can very easily solve the linear regression problem once you get this particular equation, isn't it? So we'll start from here. So I showed you the example because I just wanted to give you a very clear thought process. It was not a rocket science kind of example. So this is how I would model a single neuron model for a linear regression, right? So I would have any number of features with me. I would have a bias value, right, if required. And then obviously a single neuron model, what it does, we all know, right? Then we have to apply a function that also we have seen. So this is how this can be modeled by visually interpretation, right? So this is how it might look like. Obviously, everyone knows how a neuron works, right? So this is what we are doing as far as the model is concerned, and everyone is aware of what these components are. I hope so, right? So we have features. We can have n number of features. So associated with every feature, we would have the weights associated with it, right? So I mean, this is a little different example. If I haven't solved this, but you can always take up this, where I have shown it with the help of two variables. I hope my voice is clear. You can hear that.
Yes,
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 sir.
yes,
Yeah,
yes, we
yeah,
can
yeah.
hear.
Yeah. So, so here we have again a simple problem of plus and minus one. This is basically a kind of where we can see a classification kind of approach. Although right now I'm not solving the classification approach, but that can also be done, right? So here we have two variables, right? So the idea is, or the thought process is that we can model these kind of simple problems with a single neuron approach, right? So all we need to do is we need to pick up the right activation function, right? We need to pick up the weights. We need to pick up the algorithm, that the weight updation rule. So that is all we need actually, right? And we are able to solve these problems very easily, right? So this is just an example to show that how the calculations would be done. I'm not taking up this because we all know we all become aware of that what how these calculations are taking place, right? Everyone is aware that how these weights are getting updated, right, and all those things. So just to show it, right, that how it can also be used to solve a simple classification problem as such as well, right? As you can see that after two iterations, for example, in this particular case, so after two epochs, for example, the perceptron uh, learned the general direction, right? Because what exactly is needed? Every epoch, what we're trying to do, we are trying to ensure that the error gets diminished or becomes minimum, right? We reaches towards the target value. That's the overall purpose, right? So just to showcase an example, here in the this particular example, the positive weights on income, say suppose W1 is greater than zero, you can see, right? The weights value would be greater than zero over here, right? Over here you can see, right? You can see W1, this is W2, right? After, say suppose epoch 2, right? So what I'm trying to show is positive weight on W1 greater than 0. So it would indicate. So what I'm trying to say is that after second epoch only, you can start visualizing what is happening. So W1 says greater than 0, that is high income pushes towards approval. So this is a direction that I have got, right? On the other hand, I'm getting what? Negative weight on depth ratio, that is the W2, which is less than 0. As you can see here, this W2 is less than 0 over here, right? So again, it gives you an indication that higher depth pushes towards ejection. So what I'm trying to say over here is, I mean, these weights, although we haven't reaches toward the convergence, but starts giving you the indication. And B over here is less than zero, slightly biased towards rejection, and both features are small. So these kind of thought processes can be brought upon, right? So now what we are going to do today, again, I have taken this particular example, right? I can skip this particular example. Yeah, I can come to this. So identity function, I think I have already covered the activation functions, all the activation functions, right? So this entire session was about the linear regression. So I would be covering certain aspects because we have already covered the example and we got that thought process very nicely, right? So as you know how the activation function works, whatever it gets, it passes on exactly, right? So if it is of linear nature, the output also becomes of linear nature, right? So as you can see, the straight line equation and almost I mean this becomes a straight line equation because we have slope of 1. So it illustrates that the activation does nothing non-linear, right? So obviously in activation in identity function, uh, there's nothing non-linear happening. So if the input remains linear, the output also remains linear, right? And if we take a derivative of the identity function, right? So here I'm trying to show that a single neuron with identity activation function performs like a simple linear regression. So what I'm trying to show is that why it was so easier for a single neuron to act like a linear regression equation, right? So over here you can see if I take a derivative of it, it would reduce it to one, right? It would make it a constant because obviously this was linear itself. So obviously, if I'm to take a derivative with respect to z, it would result into one, right? So it shows a constant derivative equal to 1 for all z's. So this means what? The gradient passes through unchanged during the back propagation. That is when the error was back propagated. Although we haven't covered back propagation, but you all know what exactly is the idea that we need to minimize the error in multiple iterations, right? Okay. So So what I'm trying to say over here is, so when you use the identity activation function, its derivative is always one, right? And this means what? That the gradient passes through unchanged, right? And that helps me. That really helps me for modeling the linear regression equation or linear regression problem with a single neuron approach. In other words, if I would have taken deep neural networks, for example, or deep networks, if the activation shrinks gradients, right? For example, I'm using sigmoid or 10H, the gradient can become tiny, and this is called the vanishing gradient problem we have already discussed, isn't it? If I would have used sigmoid or 10H, it would have reduced the gradients in every step, right? And as a result, there would have been a stage where the gradients would have become what? Diminished, and that is what we also discussed in one of the sessions, that what is exactly the vanishing gradient problem is. Or if the gradients become too huge, then it can be the exploding gradient problem also. So they're both the problems, vanishing gradient or the exploding gradient problem. But over here, when I took the first order derivative, so the gradient neither shrinks or explode, and they stay healthy and stable, and that is what we needed in a linear regression thought process. So the bottom line or the entire thought process of this presentation is that why single neuron model with the same approach that I have shown with the use of with the use of identity function is good enough to model a simple linear regression problem, right? So now we would also talk about what are the advantages and limitations, although we have already done that. Where we are heading towards, we would be heading towards from here to the next session where we would talk about that simple linear regression is okay, right? But when it comes to classification problems, why a simple linear regression approach or why a MSE would fail. So we were heading in that direction from here onwards, right? So right now I'm talking about identity activation function. So obviously, why it is good, why it is advantageous in a regression model. First of all, it is unbounded, and that is what I need. Why? Because in regression, I want it to output a continuous value. I have to predict a continuous value, and for that I need a bigger range. So that range can be minus to plus infinity, right? So there's unbounded range. That's the reason. It's a simple and stable gradients, obviously, because I know that the derivative is one. So, I mean, the gradients are stable, right? So, not an issue. I can always model that very nicely because I need to model, I need to fit the line, right? Limitations are what? There are no non-linearity, no extra expressive power, obviously. If we use identity function and hidden layers, as long as this is a simple neuron model, okay. So if I would have used this in a hidden layers, so stack of linear layers collapses to a single. So I mean, use of hidden layers, it doesn't fits in very well because they again would result in a linear thought process, right? So there won't be any transformations happening with the hidden layers. So model cannot learn the non-linear relationships, right? So this is one of the, I would say, limitations, and that's the reason why we would also move towards from the identity function to the use of sigmoid or 10H or other functions, right? So solution is, if I would have thought of using the hidden layers and would have wanted more expressive power, so I would have used non-linear activations like ReLU, JLU, and many other functions are there in hidden layers, and keeping the identity only at the final layer of the regression, right? If the if there are too many complexities which would have come in because of too many variables or as such, right? So, but the final layer would always be, because this is a regression problem, the final layer I have to use as a simple identity function, right? So that I can control my output, right? So not suitable for bounded or categorical out targets. Categorical means over here, the it may not be very useful for classification approaches, right? And for the probabilities classes, we obviously prefer sigmoid or the softmax function. We all know we would be heading towards that, right? Now we will talk a little bit about the squared error loss that we are using in this particular case, obviously in linear regression. I hope you all are aware of, about this particular loss function. So we normally use this loss function, isn't it? We call it a MSE. So what is happening over here is, so when I'm training a model, right? So it makes a predictions. I mean, we know that how this model behaves. We know, right? Uh, So how do we know if these predictions are good or bad? Okay. So we are talking about now squared error loss. How how this is helpful and where it is actually used, you know? And for linear regression, we are actually using this squared error loss, right? So the neuron itself cannot understand automatically whether the predictions are good or bad. Obviously, isn't it? So we need something that can measure that how far the prediction is actually from the actual answers. So we need it. So this presentation is about squared error loss, that why it is useful and how it is useful, right? So this measurement is called the loss function, where everyone knows it, right? So obviously, I need something where I can know that how my target and how my current value which is being produced are different, isn't it? So, so small error would mean that good prediction, obviously, and large error would obviously mean that a bad prediction, right? And we all know about this particular equation, right? What is this? So this is the actual output, for example, and this is the predicted outcome, right? And square of the term is there. So this is the mean square error function. So loss function tells what? That how bad the predictions are or how good the predictions are. Both the things can be mapped from this loss function. And the gradient descent tells us what? Because I have to understand, or you all have to understand both things. that what is the role of square function, squared error function, that is loss function, and what is the role of the gradient descent. We have already covered the entire thought process. We have in the example we saw the use of squared error, we saw the use of gradient. Now I'm just picking up each every component and explaining that, right? So I need to understand both the concepts. So if anyone asks you what is the role of the squared or the loss function like mean square error, you would say that it would help us to understand how good and bad is the prediction. On the other hand, the gradient descent would tell us what, how should the weight should change to reduce this error, right? Okay. So why squared error? First of all, it is differentiable. I would also explain why we need a differentiable thing. In fact, I gave this answer previously also, because differentiable, if it is a differentiable function, it would remain smooth everywhere and it would become easier for me to optimize. I'll explain that in a later slide, right? It is convex also, right? So convex means a single global minimum for linear models. I would explain this concept also in the next slide, right? We'll take examples to explain all these terms. So right now we are explaining that why square error is preferable, right? Why not simple difference? I would have taken y minus a y dash also, but why not simple difference? Why we are preferring the square error? And obviously, one of the reasons and main reasons is that we wanted to penalize large errors. That is the quadratic growth, right? And another thought process is the statistical interpretation, that the maximum likelihood under Gaussian noise. I would explain this concept also, that what exactly. So if anyone asks you why you prefer a squared error, so it is not only about that we wanted to penalize the large errors. First of all, it is differentiable, it is convex, and there is a statistical interpretation as well. Okay, right? So we'll explain each and every thought process separately. So let us talk about the differentiable one. Why this is differentiable and how it is useful. You can hear me? Voice is coming?
Yes, sir.
Yes,
Yeah.
it's coming.
So differentiable means smooth everywhere and it is easy to optimize. So function is differentiable because of that square term. We can calculate the gradient very smoothly. I can do the first order derivative and it would not remain constant, isn't it? It would not remain constant. So neural network learns using the gradient descent. Everyone knows it. Descent needs what? Derivatives of the slope. And why square error helps? Because the square error curve is smooth like U curve or the bell-shaped curve, right? That is how it results. That is how it gives you results, right? So there are no sharp corners. So the model can easily know which direction to move on and how much to move the weights. That is how it would result you whenever you apply squared error loss. So you would always get a U kind of curve, which is very smooth, and it always gives you direction, which direction I have to move, right? And obviously, I have to head towards the direction where I can get the minimum value. So it supports us very nicely in terms of what we wanted, right? Another thought process is convex, right? If you none of you knows about it, so convex means that I need a thought process where only one value or one answer is the best solution. So if I'm using a bell curve, if it is differentiable, it would always result in a curve like this. So obviously, I need something which is one minimum value, right? I does not need many minimum values or many local optimal solutions. I need a global optimal solution. So this squared error function is convex because it produces a curve like this, right? So there would be one and only one minimum case which is possible. So it gives you one best solution. So that fits in very nicely with the thought process that I wanted to do, because when I'm trying to fit in a linear regression line, so I would prefer to get the one best fitted line, right? I would not want that give me 10 best fitted lines, right? So squared error creates a ball-shaped graph, and this shape has only one lowest point called the global minimum. So that also supports quite nicely. Why this is good? Because neural network wants minimum error. So if there is only one minimum error, then learning becomes reliable and obviously the model will not get confused very easily. Obviously, everyone knows it penalizes the large errors. So big mistakes get bigger punishments, right? So if the error is suppose one, on the other hand, the error is 10. So obviously the 10 would become 100, right? If we are squaring it. So it would be a big punishment. And that is what we want. We wanted minimum errors. So obviously, uh, we would always like to penalize the even the small errors, and that is what we are looking for. That is what we are trying to fit in the best line, so where the squared error difference is minimum. There's another statistical interpretation also attached to it, which works best when the noise is Gaussian, right? This is almost the same thing actually, and in fact this particular line is the culmination of all the top three lines, right? So Gaussian noise over here means that the most errors are small, but large errors are rare. So this very this concept is very much fitment to a Gaussian thought process, right? This actually produces the bell-shaped distribution. That means that measure of your errors lie between the most of these particular regions, and there are very, I would say, large errors which are from the extreme ends of both the sides. So they're always rare. And this is what happens in most of the data that you get. So it is, I've told you that before also, that most of the data that you get, they 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 are Gaussian in nature, right? And at times, if it is not, then we normalize the data. We try to convert into a kind of normalized data. So that is the best part of, or the best thing that we do with the data. So the data noise follows a Gaussian distribution, and naturally also in any kind of data set, unless it is very bad data, right, data follows a Gaussian distribution. Everyone knows that, right? So minimizing the MSE gives the most probable best fit model, right? So MSE, in other words, works naturally for the most real world problems, because real world problems are usually small and normally distributed, right? So obviously if someone says that where this model would be fitted quite well. So it would be fitted well in the case where we have normally distributed data, right? And MSC does becomes the standard loss function for linear regression, and many neural network uses this as well, right? This is what exactly I was talking about. As you can see, we are talking of the minimum value that is possible. So this, most of the cases when you would be trying to fit in the linear regression model, you would definitely want your data to be normalized, right? To be having a normal distribution, right? Now we would head towards a little bit about the gradient descent. Although we have learned about it, we know how exactly it works. But I would quickly again talk about the gradient descent algorithm as a part of the uh, session also. So everyone knows this particular slide I've explained before. So I would like to move in small steps. These are the steps, right? I would like to move in small steps so that I can reach to the minimum of the global minimum of the entire function. So I need a global minimum function, right? And this is the direction is also important. So direction, what is the direction in which I have to move? And then the steps. There are two things. One is direction and one is the steps. How many steps, right? So how many steps would be taken care of by the learning rate, if you remember? So learning rate would define that what is the size of these steps, so that I can move to the minimum and it does not overshoot. If my step size is very big, now I might miss that minimum, global minimum value, right? So I have to also ensure that my steps are suitable one. So I have to move downhill on the error surface to find the minimum, right? So we have already learned about this, isn't it? So I'll give you a thought process in terms of equations also. So this is a equation, and it MSc tells us that how wrong is the prediction that I told you. But now the biggest question is, how does the neuron improves itself, right? So that answer we get through what? Gradient descent. That's the process that you must remember. So answer is gradient descent, obviously. So it is an algorithm that helps the neuron reduce the prediction error step by step. Obviously, everyone knows it. It adjusts the weights bias so that the prediction becomes better. So I think I've already given this analogy about the mountain, that how we move towards the mountain and what should we ensure that the steps are not big enough, right? So I've explained it very easily. Those who may not find it, I mean, those who still are not very conversant with the gradient descent. So I've given the entire example. So suppose I have simple data, right? I have this particular data X, and this, suppose this is Y. So based on the R study, I want to predict the marks, right? So how would I start with? Everyone knows it, that I have to start with the random weights and modeling this through a single neuron, right? So this is a equation, simple, and the input suppose over here is 2, and the actual marks are over here is 4, right? And what we predict over here is suppose 2 in this particular example, right? No rocket science, right? Then I have calculated squared error, which becomes 4, so loss is large. So neuron understands the prediction is poor, obviously, right? Now we would do what? Gradient descent would start over here, isn't it? So we have calculated the loss. We would now calculate the gradient descent part. So how should the weight change to reduce the loss, right? That is what I would do in the gradient descent. So obviously it would decide whether I should decrease the weight or increase the weight, and I have to go the which direction I have to take. So these are the two things that I have to do. Everyone knows what exactly gradient is. Gradient is what? Rate of change or the steepness of the slope. So how fast something is increasing or decreasing. If anyone does not know what exactly is the technical meaning of the word gradient, right? So next I would do what is the gradient slope of the loss function actually. It tells how sensitive the loss is to the weight changes. So what I'll do is I would do, say, suppose a gradient descent update, a function like this, everyone knows it, old weight, then the learning rate, and this is the loss that I have to calculate with the loss with reference to the change in the weights, right? So this is a very simple, I would say, analogy. If it is gradient value is positive, I mean, we might move with the weights down, obviously, right? If it is negative, I would like to move the weights up. If it is large, I need a big correction. If it is small, I need a small correction, right? So this gives you a complete thought process in every iteration, that where and how to move ahead. So learning rate over here, obviously, would talk about what? How big a step to make, right?
So
So
here
just an
gradient
example.
value is what exactly?
Yeah,
Can you go back to the slide? Yes.
gradient is
Gradient value positive means
this.
exactly. Okay.
No, no,
Last.
this one.
Yes. Here
Yeah,
gradient value positive means what value exactly?
see, if the gradient value is positive, right? Gradient means this, right? If it is positive, then it gives me an idea that I should move downwards, right? That is towards, in order, I have to move my weight down, right? So that I can reach towards the minimum of the value, right? If this is indicatives, if it is negative,
Hmm.
then I get a thought process that I need to move the weights up, right? Got my point? So these are indicatives, that how
Okay.
by looking at this you can understand that, right?
Okay.
So just to give more examples, so suppose the gradient in minus 8, learning rate, suppose this is an example, right? And you did an update and you get a value of 1.8, suppose. So weight has increased over here, right? So now the new prediction over here is this, right? This is the case. So earlier, your earlier prediction was 2, then a new prediction is 3.5, actual value 4. So prediction has improved and loss has reduced. So just an example, right? No rocket science. So you can always do these things with the values and understand what is happening. And then you would do multiple iterations. Like this can be one of the examples. You can see what is happening over there is losses decreasing. So what you need to control is this factor, right? Whether you're able to. And obviously, since over here, while explanation, you have only single weight, so it becomes easier to control. So in real senses, there would be thousands and thousands of weights. So you have to manage the combination of all the weights so that the loss is minimized. Right? You got the point. So so the prediction becomes very accurate when you are heading towards the minimizations, right? So gradient descent moves downhill towards the minimum loss. So what it means, MSC would tell you that how wrong the neuron is, gradient would tell you how to reduce the error, and gradient descent would perform the continuous correction, self-correction rather, right? The important term is self-correction. You do not correct it by your involvement. It happens automatically, right? This is typical algorithm. You do not have to follow this. I mean, I mean, how you can present it, right? So how the input is. So mathematically, it might look very complex, but these are a set of inputs and outputs, right? Then output learn weights. That is what you need. You need to do the initializations, Then the entire loop starts where the convergence takes place, right? And this is nothing but this is the weight updation rule. So do not get confused with these terms. So this slide might look little complex in nature, but it is same. And this is the function, the squared minimum error function that we talked about, right? So we would move on to something called gradient descent understood, right? Um, I'll give you one of the word files also, right? I have put this into your that particular sections, right? Where that will give you a lot of numerical examples and would explain you if someone is still confused about gradient descent. So it would give you and show you the entire calculations of how gradient descent can happen, right? So now what we are trying to understand over here is what are the different types of gradient descent. So majorly we would talk about three. One is the batch gradient, other is the stochastic, right? And then this is a mini batch gradient descent. We would first talk about the stochastic gradient descent, which is the simplest in nature. Here, see what we are doing if you visualize it very carefully. We are updating, we need to update the things in every iteration, right? Isn't it? What we are doing is for every iteration in the previous examples, whatever we did, for every input, we were iterating, in every iteration, we were picking up one sample at a time, isn't it? And then we were trying to minimize that error, right? So if all the examples that I took till now was actually nothing but the stochastic gradient descent. I mean, gradient descent means what? Number of steps in order to minimize the error. So if I follow those steps one at a time, one sample at a time, then actually we are following something called stochastic gradient descent. So updates the model one after seeing one training example at a time. So I'll pick up one training example, right? If suppose X and Y, so I'll take take one training example, this particular training example, and then I would try to reduce the error between input and output till I would reduce that error till my expectation or till whatever I wanted to do. And then I'll move on to the second iteration. You got my point? It is just like taking one student at a time, improving him to whatever extent or target you want to improve him, and then you take up the second student. So if you go by this approach, this is called something called stochastic gradient descent. You got this point? So you improving the things one at a time. So each update is based on one randomly chosen data point, and each single point may not represent the whole data set. So obviously there are many data points, and you need to do this for all the data points. For every data point, you want what? For every data point, you want that there should be the difference between the target and the data point output it produces gets minimum. So if you're doing that one data point at a time and trying to, and for one data point at a time, you might take multiple iterations. Understand my point? You got my point. For example, you have taken one input like this, and then you might take more than one iteration in order to reduce the error to whatever you wanted to reach at. Suppose you wanted that I need at least 5% of error, not below that, right? So you might take number of iterations for one sample to reduce the error between the target and what it is producing in every iteration, right? So that is the concept that we use in something called the stochastic gradient descent, right? So it's very simple, definitely one at a time, but it becomes very slow also, right? So slow in the sense because we are taking too many iterations, right? Fast, why they have written updates are fast because whenever I have to update the weights, I have to update the gradient descent algorithm. In that case, it is fast, but the overall process becomes slow. Why? Because I'm taking one iteration at a time, right? Right. So updates are fast means that algorithm that the weights gets updated, you know? So you're able to update your weight very nicely, very fast, right? So this is a simple foundation example I've given you. Suppose you have a model like this, very simple. This is a loss function, right? We just substitute over here, right? Then you calculate the gradient. So it gives you what? It gives you a direction to move and how strongly to move. Both the factors have to be taken into care. And suppose this is a simple update rule, SGD update rule, for example, right? Learning rate has been given. So in SGD, this update happens after every data point. So for example, these are three data points. So I might take first data point first, right? Just to give an indication how it works. So I'll take up the first data point that is 1 and 2. So let's see. So I've taken 1 and 2. So this becomes the equation, right? So this is the epoch 1. I put in everything into it. I hope this is not a difficult thing. So you calculated the gradient and everything and you get a weight updated, suppose zero point 0.4. So weight updated immediately. So updation of weight is becoming fast. So not an issue at all, right? Then I came up with, so what I did is for step one, I did the entire process. I followed the entire process of gradient descent and everything, weight updation, everything, right? And I updated the weights. Then only I moved on to, so suppose data point two. Again, for data point two, what I did is I calculated everything. I did this and this. I updated the weights. So for data point two, I got this. Similarly, so suppose at the end of epoch one, what has happened is, so the final weights just after one pass, for example, is this. So true weights are suppose 2. So what has happened over here is I've done step 2, step 3 also. So I've reached and there were 3 data points. So I've completed one epoch. So after first epoch, I reached towards 2.2. I reached towards 2.2 this weight. So true weight was 2. So there's a difference, right? So then I would reach. Now I would start again this second epoch. I'll take up all the examples. So how I completed it, how I proceeded it. I took all the three examples in one epoch, right? And then calculated the entire error, whatever. I calculate the error for each and every iteration also. I calculate the error here also. I calculate the error here also. I calculate the error here also. And then everything was done. And then I took a difference after epoch 1. I found that there is a difference, right? And I need to go further. And then I would start another epoch. So how I'm doing is one data point at a time, right? Isn't it? One data point at a time. So AGD already overshoots slightly normal behavior. It actually looks like a zigzag. So at times it may happen that in after epoch 1, the error is 2.256. Next time it might be very less. It might be suppose minus 1 or 2, whatever it might take place. That so it might move in a zigzag fashion. That is what it is trying to say. So each data point pulls the weight in its own direction because when you're doing it for each data point, so some weights might pull it in one direction, at some other iteration, it might pull it in another direction. So the some weights are overshoot, some are undershoot. So the overall effect, what it produces is a noisy path, zigzag movement, but obviously progresses are very fast because weight updation is very fast. So this is what is a very simple explanation that you can get out of from SGD, that updates are very fast, low memory required, right? It escapes the local minimum, right? And learning is happening live, right? You don't have to intervene in between, it happens automatically. Issue is the noisy convergence. One sample is not at any point of time would be a representative of the whole data, right? And since we are updating it one at a time, so one at a time it might move, at times it might move towards positive, at other times it might move towards negative, and then it does not represent the entire data, right? So you will never know that what exactly or where exactly you're heading towards, right? So there might be many overshootings, many oscillations might take place, and you might take quite long to actually converge, right? So you need a lot of tuning is required, and still after tuning you may not reach anywhere. So the solution of this is that we do something called batch gradient descent, which is more
Sir,
common and which is, yeah, yes,
sir,
tell
a
me.
quick question. Yeah.
Yeah,
Sir, I have 2 points. First is
yeah.
in lecture number 2, you helped us solve AND gates or gate with it, right? In that, also, when one row is whole executed, you update the weights and then used it in the other iteration, not other iteration, other sample of the data. Like if you have two variables X and Y, 000111011, you
Mm-hmm.
solved 00 row, and then you
Mm-hmm.
updated the weights and then you in the 01 and then 10 and 11, right? Am I
Obviously,
right?
yes,
Yeah.
yes, yes.
So can we call this like SGD in that manner? Although it was not using gradient
Yeah,
descent
it is
formula.
SGD also. Yes. All the previous
Okay.
methods till now, whatever I explained was SGD approach only. Yeah.
Okay.
I've had,
And in slide
I've
49,
not done, yes, in slide,
sorry, and
what?
in slide 49, sir, next slide, you mentioned
Mm-hmm.
escapes local minima because of the
Yeah,
noise. Slide
yes.
49.
So what happens is I've give you a very simple example. If suppose my algorithm behaves like this way, right? It might. So escapes local minima, noise helps. So what happens is since I'm using this one iteration at a time, right? So obviously, if this is a local minima, right? If this is a local minima, isn't it? These are all local minima. Global minima is this one in this particular example, isn't it? Don't, I hope you
Mhm.
understand what exactly it means.
Yes, sir.
So this is an advantage in this sense because when I take one iteration at a time and send one sample is not a representative of the entire data set, right? I've just done
Mhm.
one sample. So one sample would not affect because one sample would I would always not get stuck into local minima because one sample does not dictate everything, right? It is a combination of the entire data set that would dictate, right? So I would never get a possibility to stuck into this, isn't it? If all the data points are behaving the same way, then it might get stuck, but not all the data points would behave in the same manner. What I'm trying to say is, see, uh, decisions are not based only on a single data point. It is a collection of all the data points, whatever there, right? So even if one of
Mhm.
the data points gets stuck over here, doesn't matter for me, right? So that's what
Mhm.
it does not. I mean, it does not create a problem which might be created by others, right? So that is one of the examples, or that is one of the advantages I would say, right? But the
And
idea is
one
that it oscillates too much. Yeah.
Okay, one
Yes.
more maybe stupid question. Sir, we have been learning that in linear regression, we'll have one local global minna using,
Yeah.
in the linear
Yeah.
regression using it.
Yeah.
But when we get an explanation, we come to know the mountain-like structure and we need to
Yeah.
find local and global. So I'm bit confused on whether we are using, I mean, linear regression type, should the graph be like one U, like
One,
convex,
one
or
you. Yeah. It is same thing. You present it like this way, you present it like a mountain way, right? Anything. So here also you need a why we do not use mountain structure most of the time, because otherwise we have to use the word called maximize, right?
Hmm.
This structure is more suitable because we're heading towards a minimum value, right? So gradient descent talks about minimum value to be achieved, one global minimum. Here also it is one global maxima or minima. When you talk about maxima, you do it in a reverse direction, then you call it minima only, right? So that's the reason. So don't get confused with mountain and this. The concept is same, right? How do you reach and what steps and what direction you have to move, right? Okay.
Okay. Thank you.
Sir, sir, I have a question.
Yeah. Yeah. Batao. Yes. Yes.
So, so sir, like in gradient descent, for a epoch, do we consider all the records of that epoch, or is it like it's
Yes.
skipping randomly?
No. 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 We do not skip. We have to take all the all the steps, all the points, all the data points.
So, but then how come it is different from the normal gradient descent, sir? Because in normal gradient descent also we take all the records.
So
But
that's
in
what I'm trying
SGD,
to say. No, that is
yeah,
what I'm trying to come up. The gradient descent, there are three types. That's what the first approach that we did, that is SGD. It talks about all the data points and it talks about the way till what we did, right? Now I'm explaining the batch gradient, so that might give you some of the answers that you wanted. So how it
thanks, sir.
works and yeah.
Yeah, I have a
So
follow-up
how
question.
does yeah?
Sorry, sir.
So how does
So, sorry.
yes, yes. Mm.
So when, I mean, since the SGDs are producing noisy curves, like how we will understand when the curve is getting converged, like algorithmically as well as graphically, sir, in
Epoch
geometry.
wise, see, that is what in the previous examples also what we saw. We we evaluate the things after one epoch, and in one epoch all the data points were considered, right? So
Yeah,
what happened? So we computed error 1, for example, here. So after epoch 2 we considered error 2. So here also all the in data points were there. So then we compare error 1 with error 2 completely.
okay,
And in between also, what we did is in every iteration, I computed the error for first data point, then moved on to second data point, then moved on to third data point, then fourth point. So in every iteration, I am calculating the error also, right? But when I start comparing from one epoch to another epoch, that is where I make a decision, because I need a place, I need a iteration or an epoch actually where all my data points are correct.
okay,
It means for all data points, there's the difference between the in the target value and the produced values are same.
zero.
I mean the
Yeah,
error are zero
yeah,
or no errors. That is what we learned previously also, right? So
yeah,
the why it is called stochastic, because we are doing it for each data point, right? We are doing it, we are calculating those errors for each data point, and we are waiting for a situation where for each all the data points are with respect to target data point, they have the zero error or whatever, or the minimum error that we want to produce.
So
So
after
therefore, yeah,
yeah, go ahead.
yeah,
So
please.
after each data point, we calculate the
Hmm.
mean squared error, and according to that, we
Obviously,
update the weights and bias.
obviously, that is what
Okay,
we do
so
now.
okay,
That
yes.
is
So
what
for
we were doing.
example,
Yeah.
XOR gate we have in which we have
Hmm.
like two input sets 0 1 1
Hmm.
0 1 1 0 0,
Hmm.
and this
Hmm.
after calculating for first round, that is 0 1,
Hmm.
we update the
Hmm.
weights and bias on the basis of
Hmm.
mean squared or the gradient descent, and then we keep on
Hmm.
doing it.
Yes. That's what we did, right? See, in the I'll explain. I'll give you more suitable example. Suppose there is a data point x, and this is the y, right? So what we are doing. So when we talk about stochastic, so how it is little different. Understand this. So there must be some value, right? Maybe a and b value, right? So what we are doing is for this input, I wanted to that it would produce some kind of y dash also, right? And the target value suppose y. So for this particular given input, we will produce a y dash. Then I would try to, and there would be a kind of error that it would produce, error e, right? So I would iterate it till a stage where this error comes down what I expect. So that number of iteration that I would go along with this particular case, individual cases that I'm bringing about. So I'm handling one case at a time, right? So when I would remove this error between y dash and y to the extent that I wanted, that is called stochastic, right? Okay, you got my point? Because y dash and y, the difference between them needs to be minimized, right? So when this error would get minimized to the extent that I wanted, I would I have to go through multiple iterations in that particular case. And that is what I showed you with example also, right? So one at a time. So whatever you took it as a one at a time. Like understand this batch gradient. So you might get the difference between what I did between the this stochastic and how does the batch is different. You might get that difference entirely into your mind, right? So here, just let's do this first, and then you would try to understand that what's the difference between what I did before and what I did now, right? First, try to understand batch gradient now, okay? And then we'll compare with what I did in the previous example. So in the batch gradient descent, the model parameters only after looking at the entire training data set. In the previous case, suppose I had three data points that I took. I took one data point, then the next data point, and then the next data point, right? Okay. Over here, the uh, the entire data set I would look into and see that what happened, right? So in the examples of X, I mean, or and we did a kind of batch gradient descent also, right? So we would not do any partial updates, no intermediate corrections, no update. One full database pass would take place, right? How it takes place, let's do the same thing. And then we'll compare it with what we did it in the previous example. So here what I do is I took this particular example, right? I took this error, I took this gradient and all those, right? And then calculated this value, right? I have just took the gradient part of it. I haven't calculated the error. You're getting my point. I have just taken this gradient part. I haven't calculated the error. Then I moved on to data point 2. And in this particular example, my data set contains three data points. My sample contains what? Three data points. Same. Let's come to the previous example. What we did? What we did is this was the stochastic. We for the data point it took, I calculated the gradient. I did the weight updation rule right now. You getting my difference? And updated the weights immediately. Did anyone got the difference? I did the gradient.
Sir.
I calculated the weight update also. You got my point? Again,
Yes, sir.
then I went to data point 2. Yes, anyone? Anyone
No, sir.
wanted something?
No, sir.
You
I'm
got
good.
my point?
Yeah.
So here the weight updation was done immediately for the same data point. Now coming back to what I did over here. So here I'm not doing the weight updation. Understand my point. See, weight updation is the major thing that we do, isn't it? To shift the error here and there. So I did a gradient. It would only give me a direction. I came to data point 2. Again, it gave me a direction, right? Again, I came to that data point 3, gave me a direction. Now whatever I would do is for the entire data set. I mean, I would do something with these points for the entire data set, that is the entire 3 points, not in between. So what I did is now I took a average gradient. Previously, what I was doing was I was doing it for each and every data point. So I took this, then I did the total weight updation. Did anyone got the difference between the two? What is happening? So end of
Yes, sir.
so
Yeah, got
after
it.
the end of one batch gradients, only one update was done. Previously, all the updates were done for each and every input. So, so it was based on all the data. Direction is accurate, and so it becomes more accurate. Hello? Because previously it was a lot of oscillations. All the three data points would might oscillate. One in left direction, one is right, and again in left. So over here, since I'm taking consideration of the entire data set at once, So it might help. So no randomness, gradient is exact, every step is carefully calculated. So it might give you a direction like this. So you left side you are underfitting, right side you are overfitting, and bottom side you are actually getting a minimum error. So the curve shows how the error changes as the theta changes, right? So the idea is, I mean, it depends, right? I mean, some data points, if the data points are very small, you might have a stochastic works quite well, and so it
Sorry,
depends
sir.
upon how, yeah,
So there's a difference
yes,
between the SDG and the batch gradient descent,
yes,
isn't it, sir?
yes. Now we are left with one more. Let's come to that also.
Sir, one question. Can you go
Sir,
back?
sir,
हाँ बताइए.
please.
Yes.
Here you're saying that this bridge gradient descent, this is not converging, rather it is going up. So why
So
this is
obviously,
shown?
see, no. See, what is happening is, because if it will go towards left, say after one iteration, right? See, after, for example, after say suppose one iteration of, suppose I call this as a epoch one, right? So epoch one, after calculating all this, right? So it would give me a direction. I might reach towards here, and next epoch might give me a this. So what I'm what is happening, that difference between two is getting minimized, right? So I know that even if it oscillates too much, even in every epoch, if it oscillates too much, so I would actually reach towards minimum, right? Earlier it was what? Earlier it was like if I give a direction, it was moving here and there. I do not know where it would move, how it would move, and towards end also I did not know that how it would move. So here, that difference, what is this? This is a large error. This is a small error. This is much smaller error. So it is able to converge in a better sense when I
So
talk
the
about.
arrows are maybe in the opposite direction then, right? Are we
No, I
the
mean,
arrows which
see,
are
this, I mean, see, after one batch, for example, I got this, I mean, after calculation, all those things, I get a weight like this. So next iteration or the next batch might give me another weight. So since all the updates were done for the entire data set, right, it helps me move towards a direction which is moving towards the minimum
minimum?
gradient, or sorry, the minimum value, right? It gives you a more balanced approach. In the previous case, what was happening is that for every data point I move here and there. It was a zigzag movement, right. In the previous approach also, or here also, ultimately it might take too many iterations, we would reach towards minimum, that is for sure. The way gradient descent works, it always allow me to move towards the minimization. That is for sure, right? The only difference is how many steps you invest, right? So the difference is that when you talk about batch gradient, it might take lesser number of steps. It would be a controlled version. When you take the different approach of, so suppose, stochastic, it might take too many iterations. That's the difference. But you would always reach to the minimization because the algorithm is gradient descent, which would always minimize the function. You got my point? So it's not that, it is a more controlled version, nothing else. Got this?
Yeah.
Huh.
Um, but
So
sir,
yeah,
in
yeah.
SGD, wouldn't the
Hmm.
last data set influence the gradient descent more? Whatever the
Last,
last data set, like let's suppose you have
no,
3 points,
no.
right? In SGD,
Um,
so
just wait,
whatever is the
just
last,
wait.
yeah,
You're talking about
whatever is the last data
in a
point
way,
on which, yeah.
not exactly, because yes, in a way, yes, it is a cumulative effect. What you're trying to say is, I understand that you're trying to say
Hmm.
that data point one would affect data point two, right? Then data point two would affect data point three. Yes, in a way, cumulative manner, it is getting affected, definitely,
And
right?
wouldn't the uniformity of the data would be an issue here rather than in batch?
Why? Because we are considering a case where all my data points in one epoch behaves uniformly. I'm looking for that stage now, so not an issue.
Mm.
I'm
Okay.
looking for a stage when all my data points. So that's the reason I told you that even suppose three of my out of 4 points, three of my data point gives me exactly what I wanted, but one data point is still deviating. So I have to still
Mm.
wait till iteration where all my data point, four data points starts behaving in the same direction. I mean, in the
Okay.
same way, right? So that's the reason I'm
And
telling you that SGD might take more number of iterations as
mm.
compared to SGT, right? Stochastic might take more number of iterations. You do it
and epoch,
experimentally also. Yeah,
sure.
epochs
And
only.
epoch
That's
zero may not epoch zero may not necessarily give the same result on epoch zero and epoch one for
obviously,
batch
obviously,
and okay.
obviously.
Understood.
So there is another thing which is a mix of both. So in a mini batch gradient descent, model updates the model parameters using small subsets. So rather than entire data set, so we might form a subsets. So subsets of two, four, even numbers of subsets mostly, right? We can have a batches like this, typical batches. So not the entire data set would get updated, but this one. So it's a kind of adjusted mechanism of batch gradient actually. So mini batch. So what we need is mini batch size that needs to be defined. So it might work better in some cases. So batch gradient descent we talked about was a stable and too slow at times. Again, the batch gradient also becomes too slow. SGD we talked about that fast and too noisy. And mini get batch actually balances both. But it depends. Like I mean, what data would fit in for both all the three cases? It depends. It might happen that the stochastic might work better for your data set at times, right? So just to give a thought about this, you might define this B. This B would be a mini batch size that you decide. For example, 2. So here, suppose I have, if I decide that this would be a size of 2, then I'll do it for only sample 1 and 2, for example. 2 is the size. So I'll take the same thing, right? I'll take this and then I'll update the weights. So these weights would get updated for the two batches or the two samples. And again, I would update for batch two, for example, 3 and 4. So same thought process, but a mix of both the approaches. So mini batch, I haven't seen too much in the books where mini batch is preferred. So either the stochastic or I have seen this batch gradient works. So mostly batch gradient works quite nicely. That is what I have understood, right? So why mini batch works so well? Because computational efficiency uses matrix operation, GPU friendly, anything that you have to do the experimentations. I'm not very sure that what data set would prefer and how each of the data sets would behave, right? So it's a lot of experimentation work gets involved. But yes, in standard books, you would often see batch gradient method to be more common one, right? So, I mean, this was about the gradient descent and its type. What I have given you is a file also, which would be a very important file like this one. I put this file in your folder. This is a very important file that you should go around, right? It would give a complete picture. Those who might have missed out. So I've explained the gradient descent with a very perfect example, like you can see. And there's something which was missing in your presentations also, so I didn't covered is like I covered something. Then I covered this stochastic gradient descent. So those who are not able to understand it, I've gave the analogies also, all those things. So you would be able to understand it through this also. And then I also have covered something called, which is more important, which you also see in algorithms. There are something called, let me explain you. Yeah, this is what we have already done, right? So mini batch I have done. I've taken examples also, right? So you can see this example, right? In case you get little confused, so that you can, yeah. So your presentation didn't cover this. So also read this is very important. Momentum methods, right? So where you would start talking about uh, something called, you must have heard about adaptive methods, right? And algorithms. You must have heard about something called have you heard about these types of adaptive, that is ADA grade and all those? So just go through it, although it was not the part of the syllabus, so I didn't cover it. But these are very important things, right? So in case you have any difficulty, you must have heard about root mean square propagation. So these are also different optimization algorithms which is a part of it. So anyone who have used machine learning, they must have seen these algorithms at the back of it, isn't it? So go through it, it would help you, right? So what we'll do is we'll move on to the um, something called the next presentation, that session 4, which was supposed to start today. So I'll cover this in the this particular aspect, right? So in this particular session, the idea was to be thrown on classification. So we covered regression, and then we are covering the classification, and then from the next slide we will start actually touching upon the backpropagation neural network, which is the most important concept, right? So this is not a big, these are all the concepts which I'll be covering right now are very simple. So we can, do it little fast. Everyone knows what classification is, right? Is a supervised learning task, and what we need to do is instead of a continuous value, we had a category that we need to predict, isn't it? Or a class label that we need to predict. Everyone knows that what are the characteristics, right? We have input, we would have the known output classes. These classes can be, if these classes are two, we call it binary. If these classes are many, it becomes a multi-class problem, right? And goal is that for a given input, we have to assign one class to each and every input, right? So difference from regression, everyone knows it, right? A number of examples. I hope everyone is aware of it. There are a lot of examples on classification that everyone knows it, right? Whether spam or non-spam, these are two classes. Medical diagnosis, whether the patient is suffering from a disease, yes or no. Again, a binary class. There can be n numbers of diseases as a class that becomes a multi-class problem. So I hope everyone is well aware about. So binary classification, everyone knows it. Multi-classification problem, everyone knows it. We have multiple classes. You can name those classes. You would have classes, suppose A, B, C, D, E, right? Similarly, the digit recognition is a perfect example of multi-classification problem where we have 10 classes, right? There can be multi-label classification also. Multi-level classification means that each example can belong to multiple classes simultaneously, right? So, for example, a given input might belong to class A as well as class B. That can always a possibility, right? Like movie genres, right? So, some say, single document might belong to category A as well as also belongs to category B, for example, right? So, multi-level classification is also a possibility, right? Everyone knows how do we define binary classification, right? So it has two sets of values and boundary. So normally what it does is that, suppose for a given input, we produce a probability, right? By having a function fx. What is the probability? So we produces the probability in the range of 0 and 1, right? Okay. The function we produces, it produces a probability between the range of 0 and 1. And then we apply some kind of decision boundary. And that decision boundary can be zero point 0.5, for example, just an example, a threshold value, that all the values left to the zero point 0.5 would belong to, say, suppose class 0, and all the values, uh, to the other direction greater than, suppose, zero point 0.5 would belong to a class 1, right? So this is how, by doing a thresholding, I have converted a simple probability based model into a class based model, right? So this is normally what we do in binary classification problems, right? I mean, this is a simple. So this decision boundary has to be formulated, right? So decision boundary I have divided that. This is suppose at zero point 0.5. So beyond one region that would be region 0, and beyond one region that would be belonging to region 1 or whatever. So we might give any name and example to these boundaries. So, I mean, the problem with linear regression for classification that we would understand, because you know that linear regression, the outputs are in the range of minus infinity to plus infinity. So, I would not be able to draw that threshold or draw that boundary line very nicely if my region is minus infinity to plus infinity, because because I would prefer that I am able to draw a boundary into a positive region of suppose 0 and 1 in the form of a probabilities, right? I can draw a boundary in this direction in somewhere, wherever. Not zero point 0.5 was just an example, right? You could have any boundary or any threshold that you could have decided, but obviously that decision boundary to be drawn in minus infinity to plus infinity becomes much bigger challenge. We would talk about this more details in the coming slide, right? That why linear regression approach may not be suitable enough for doing the classification, right? We would talk about that in more details. So what is required is we need to convert this into from this approach to the more suitable range approach, and this can be very easily done. How can I do this? Anyone? I want to bring all my values in the range of 0 and 1, right? So can anyone suggest
Activation,
something?
activation
Yeah.
functions and
So
sigmoid.
so we could have
Sigmoid
used
function.
sigmoid
Yes.
activation function would have been a more suitable approach. So that is what we would be heading towards it. That how this sigmoid activation function can be used for logistic regression. This is the first binary classification algorithm that we would do. So let's I have drawn a little bit more attention of yours that why linear regression, why not we use linear regression to solve this classification problem, right? We must have a very clear thought process into it, right? So suppose I have this particular example, right? Classification problem, right? Whatever is the x, just forget about this value of x. So, and these are two classes. And I try to solve it through something called linear regression problem, right? So what I'll do is, if I'm, say, suppose this is the equation that I have formulated, for example, right? So for every x, I would be putting this. So you see, these are the possible kind of values that I could see. So obviously, minus 3 is not a valid probability. 1.5 is not a valid probability. So probabilities cannot be less than 0 or greater than 0. So obviously, it becomes difficult for me to actually map in terms of probabilities, right? And no matter how good training is, large inputs will produce huge outputs and small inputs will produce negative outputs. And linear functions cannot naturally model the probabilities. That is for sure. So one of the obstacles why we did not use the linear regression model, because I was not able to model the probabilities through this kind of thought process, right? So this is not the only problem. Another problem was that non-constant error variance, right? In classification, the target values are in the range of 0 and 1, definitely. But linear regression assumes what? Errors are normally distributed, which is not possible in classification. Why? Because suppose I have 10 samples, so it may happen that 9 samples belong to one class and one sample belong to another class. So by any means, that normalized distribution or normal distribution thought process is not applicable in classification approach, right? But here in regression, as I told you previously also, the errors are normally distributed. That's what we, because most of the errors, the bigger errors on the boundary conditions are rare. And small errors are always accumulates into a particular region, normal region. So the constant variance classification actually violates or data violates these assumptions. So obviously the fitment is not possible, or linear regression approach may not be good enough. So linear regression model assumes breakdown, right? So we would talk about logistic regression, obviously. So logistic regression is the first classification model. It might confuse you because it talks about regression, but logistic regression is basically a classification approach. Why it is called, why it has used regression? Because it uses the simple linear regression model also into its entire thought process, right? So that's the reason they have used the logistic regression. So they use, so we would apply the sigmoid function on the linear regression model that we have studied so far. So far, this is a linear regression model that we all know. So we would just apply the sigmoid function. So this sigmoid function would actually convert the output. This output is between minus infinity to plus infinity that we know. So it would convert this as into an approach where the output would be in the range of 0 and 1, which is very, very suitable for the probability expect. And then I would use something called, which I told you that I can use a threshold kind of concept here where I can decide the decision boundary between the range of 0 and 1. And since this is a probability based thought process, so I know that the wherever my boundary would be put, it would be consistent, right? So over here, someone might ask why these exponentials, what exactly is happening, right? So what is happening over here in this case? This was the linear model that I was using. I was just I've just fed it this linear model, or have embedded this linear model into the sigmoid function, nothing else. So why exponential appears? Because it comes from the exponential growth or the decay mathematics, obviously. So if you can see Z, that is this Z, which was a regression equation. If it was large negative, it would convert into near zero. If it is zero, it would bring me to a point 0.5 always. And if it is large positive, it would bring me to the near 1. So why is sigmoid is smooth? Because sigmoid is continuous, and the most important part is that it is differentiable everywhere, right? In every region. And this is an important because why this is important? Why differentiable? By being a differentiable, it would be important. Anyone? I explained
to
that before
reduce
also.
to reduce the loss. So because we are
Because
changing the gradients.
exactly, yeah, because we would be using a gradient descent where we wanted to update the weights, we want to control that loss. So unless it would be differentiable, I would not be able to do that. And that was one of the biggest drawback with the regression, because when I would do the differentiable part, or when I would do the further derivation, it would result in a constant value, right? So obviously, by now you all are aware about these things. So gradient descent requires derivatives, and without derivatives, weights cannot update and back propagation would actually fail. So this is gives you a little bit of thought process here. The sigmoid is outputs the probabilities between 0 and 1, and the sigmoid derivative, it actually gives you a maximum value at 0.5, in fact 0.25, right? It would give you maximum value at 0.25. I'll explain how does it came, right? That it is sensitive to the input. So how do you change the inputs? It is very sensitive, right? When you do a derivative of it, right? The sigmoid derivative, right? So see how it comes. So why the maximum derivative is 0.25? So we know that if I give an input to a sigmoid as 0, it would result in 0.5. But when I'll do a derivative of it, it would result in a 0.25. So you must know from where this particular 0.25 came in. So when the input to the sigmoid is 0, we always get zero point 0.5. It means what? That 50% probability. The model is completely uncertain about class 0 or class 1, for example. So if it says zero point 0.5, everyone also understand that what does it mean? It means that the model is confused, right? If it is zero point 0.3, you can't say that the model is confused. If it is suppose zero point 0.6, zero point 0.7, you can't say the model is, it is inclined towards positive side. It is zero point 0.3, it is inclined towards suppose class 0, but not in the case of zero point 0.5. So that becomes a kind of boundary making decision. So why derivative matters in classification? Because when I would be doing, everyone knows it, right? So derivative would tell me that how much should the weight change, right? So I've given you little bit of interpretation of the bell curve also. By now you all have got that understanding actually. So so when you get so suppose this kind of probability by putting say true class and you're getting a probability like this. So there can be a case now the model is already confident, right, in this case, and suppose here you say that predictive probability is suppose zero point 0.9, another case the predictive probability upon true class is 0 in this one. So derivative becomes near 0 here, right? So only tiny updates are needed. You see, when you say understand these two cases, this is case 1 and suppose case 2, right? So when the derivative when you do these cases, right? So now the model is already confident, obviously in case 1, right? So derivative becomes near 0 means that only tiny updates are needed. This prevents the unnecessary weights changes, right? So obviously this would when I do a bell curve or when I am interpreting a bell curve, which I would be able to explain in the next slide also. So there could be a situation like uncertain prediction. That could be a situation like confident prediction, right? So when there is uncertain prediction, when we are towards these regions, we need a strong learning, right? And when we are confident prediction, so suppose weak learning, so it means that learning strength is suppose weak. So bell curve actually acts like a adaptive learning controller. It automatically decides. I give you more. So you getting my point. So bell curve when I would be towards, I mean, in this particular region, for example, in this region, so I know what is happening when I'm towards both the extreme regions. Then I know what needs to be done. So accordingly, my weights would get changes and would get a update. So whether it needs a tiny updates, whether it gets more updates or more positive updates, that is something which can be very nicely interpretable through the bell curve thought process, right? So properties of sigmoid function, everyone knows it. I mean, this was there in the slide, so I doesn't want it to cover. Everyone knows it, right? So when this everyone knows about it, right? I've already spoken. The four components everyone knows. This was a part of the slide, so already. So there has to be the data points, right? There has to be a model that we would do it in the form of single neuron with sigmoid. There has to be an objective function, for example. Now we would also talk about that why this binary cross entropy loss is important. Why we have suddenly started talking about a binary cross entropy loss. Why not the same loss function that we did MSE was useful, or why MSE would fail over here? So we would talk majorly on that aspect first, right? So that you all are aware about that how does this binary cross entropy came into picture, right? And then obviously I need some kind of learning mechanism, not necessarily that stochastic, it can be batch or whatever, right? So So, I mean, this is how data is represented. Everyone knows data can be represented single dimension, or it may be required. We need to represent the data in a complex form as well, right? So, yeah. So this is how I can model binary classification, a simple binary classification through a single neuron model, right? So everyone understands this. So the most important part is the activation, and this is something we always know that what it does, right? So what it is doing, everyone knows it. What activation function is being applied, everyone knows it. Z, we normally call it as a logit function, a logit, right? Let's talk about then. We have already explained about this, right? What is happening? So yeah, we can do a small example also just to get an understanding if few of you gets have some kind of confusion. Suppose you want to predict whether a student will pass or fail, for example, right? So feature is suppose hours studied, and another could be suppose attendance, for example, right? So if this is a sample value, for example, just to get an output, and this is sample weights that we have taken, for example, right? So I would do the input right first. Though for those who are not still a little out of touch and not able to get through the theoretical part, so that's the reason I put in this particular example, so that explains the logistic regression through a working example. I always prefer to give these examples because that gives a clarity into your mind. At times, theoretical things doesn't gives that clarity. So then, step two. So I mean, these steps are gives you a very clear picture on how logistic regression works, right? So then you would do computed weight computations. So this is Z. Everyone knows it if you are well aware of it, because the neuron would take the summed input, right? And this is how I have formulated the equation. Then we would substitute this, all those values, just forget about it. I hope everyone can know it. Then the step three, you would multiply the terms, you would get first term, second term, you can do it. Then you add up both the terms, you get, say, suppose that. So this is a neuron's raw input after the first step, right? Then you apply the sigmoid function and then you get some value, right? So you get something around this, and then you can apply the final calculate the exponential part and everything that you can do it, and then you apply the final probability, whatever, and then you get something like this, right? So the final answer suppose is this. So it says what? 96.8 probability that student will pass, and the classification decision would be it is suppose greater than zero point 0.5. That was a kind of threshold I took, just one example. So it was class 1, right? So this is a very simple example. If anyone hasn't followed it, they can do it. Now, now our direction of understanding would move towards that why not squared error for classification? Why we are trying to change, because I use that I would be using a cross entropy rather than the squared error function. Why not I am using MSE as a loss function, right? So we would have some understanding about it, right? So first understand about these two terms, convex and non-convex, which is also important. So convex function is what? Function which has only one global minimum, like over here, we have one global minimum. So obviously in this case, if you remember in MSc also, uh, I mean, these things was pretty easier to handle. Gradient descent was smooth, because it needs to reach towards one minimum value, and this is called ball shaped. This could be one of the simple examples. On the other hand, the non-convex function is what? It might have multiple valleys, multiple local minimas, flat regions, saddle regions, right? So optimization becomes much difficult. Obviously here the optimization is much simple to handle. So gradient descent may get stuck when we have a non-convex function. It moves slowly and converges poorly also. So non-convex function is something which can be difficult to handle. That is understanding that you need to take. Now, when we do MSc, right? If we using an MSc, it was a pure convex, not an issue, right? If you remember, this produced a quadratic ball shaped, so it was very good property of convex, and it was much easier for optimization, right? Now, what is happening over here in logistic? So logistic regression adds sigmoids, and the moment you add sigmoid, everything gets destroyed, and everything changes the entire concept. So when you do a sigmoid, so it becomes very difficult. For one input, it can have this, the two label can be y, and bias can be this, and z is equal to w. Prediction could be like this, and this could be a simple thought process that I've given. So suppose once you use sigmoid. So I've computed certain values for this particular example. For this particular example, let's compute certain values with the sigmoid. So suppose w when is minus 10, it gives you this value very high. When w 0, it gives you 0.25. When suppose W5, it gives you 0.00, this one, very low, right? So loss decreases very slow at extremes, very fast at centers. That is how you can, I mean, this is the outcome, you can say. This is the summarize. So when these are extremes, when this is an extreme case, right? And similarly, this is an extreme case, I can say. And these are the, if you can take many more examples, right? So it says that very slowly at extremes. See, this is a very high, and this is this, so very slow. So very slowly at extremes, very faster at center, and slowly again and slow again near optimal. So it actually gives you a very irregular curvature, not a clean ball that we talked earlier, right? And this actually would result in, so suppose W minus 10, this one. So it says that true level was 1. Here the true level was 1, and the prediction is this. This is a very different approach and wrong approach actually, right? It says that true level is 1. You get the predicted this. There's a huge difference between the two. Error is very huge, but but the derivative becomes very tiny over here. When you would take a derivative, it becomes, when I showed over here, it becomes very small. So it says that you have too much of error. So suppose student gets a very less number. It is similar to like a student gets a very less number, and still you say that no, you just need to do this only, and you're able to pass. No, because there's a huge error. So you need a huge correction into that particular student, but you didn't suggested that correction, right? So here the second derivative, the derivative actually does not helping him, right? So gradient descent barely moves, even though the prediction is terrible. I'll give you more example. So in other words, if we have linear regression plus MSE, so you can see that very nice curvature and smooth gradients would happen, right? I would reach towards a minimum value, right? If I use MSE plus sigmoid, so there would be a flattened edges, right? It would have flattened edges, changing curvature, weak gradients. So optimization becomes very difficult. So that's the reason. So the role of the second derivative does what? The second derivative tells the optimizer how sharply we should move. So that is where I'm not able to get much good results when I'm using MSC plus sigmoid, right? If I'm so the question was here, boy, why I was not using MSC, and why I'm certainly talking about another loss function. So so the convex, if it had been a convex bowl, the second derivative would have been a constant stable movement. But here the second derivative changes dramatically, the large in some regions, tiny in small regions and other regions, and inconsistent curvature. So this actually technically confuses my optimization. So that's the reason why, I mean, we are not going for MSC as a suitable loss functions. So the problem with sigmoid derivative is what? When the prediction becomes extreme, so even the large error is huge, and the derivative multiplies it by a tiny number like this one, right? So what does this mean? The model says you made a huge mistake, but gradient says update the weights only a tiny little bit. So this is not a good behavior. That's what I gave an example, real analogy also, that you scored 1 out of 100 in exam. Teacher says only improve zero point 0.1 marks next time. So this is not good enough, right? And that is the reason why we are not using something called the squared error function or the squared error concept for classifications. So I hope this would have given you much thought process. So suppose one model makes a very wrong prediction. Example model is saying that I am 99% 9 show that the class is 0, but the actual answer is class 1, for example. So this is a huge mistake, isn't it? So ideally, the learning update should be very large, but the it does not says that, right? So so this is how you should be very clear in your thoughts that MSc would fail, right? So why gradient descent suffers? because gradient descent depends on the slope, right? Then updates becomes tiny and almost no learning happens. And why cross entropy avoids this? Because cross entropy derivatives becomes like this, right? We would understand this also. So there's no multiplying by sigmoid derivative. And therefore, even the wrong confident predictions will produce a strong gradients and optimization would remain efficient. So that's the reason why the cross entropy is able to solve this much nicer. You get little bit more understanding of this. So cross entropy would remove this problem. Why? Because the gradient simplifies it to this factor, right? I'll show you the cross entropy function also, right? So the only the error remains, right? There's no extra sigmoid derivative multiplication which is there, right? So now the model says that I made a huge mistake, and the gradient also says that you make a huge mistake. So exactly that is what we wanted, right? So in a very nutshell, you can say that when you use MSE plus sigmoid, you have a wrong predictions, sigmoid derivative shrinks gradient and a weak learning. But in cross entropy, your wrong prediction means large gradient preserved and the strong learning. So this actually helps me, right? So in the next, so this is how, I mean, a cross entropy loss for a single neuron example would look like. So this is the complete function that you must know when it comes to the cross entropy, right? So, so I mean, here you can see that when it is 1, the loss is this one. So you penalizes it if it is far from 1. And if it is 0, the loss is this. Again, it penalizes it if it is far from 0. So that is what you wanted and becomes a more suitable thought process, right? This is the average cross entropy loss. So we would be using this now for the next, I would say, understanding what we are trying to do for the logistic regression, right? So advantages you can say it is first of all the probabilistic interpretation. It is derived from the maximum likelihood estimation. You know. I would rather do one thing. I would try to cover some beautiful example on maximum likelihood estimation. This PPT does not contain that, but I will try to cover one beautiful example on maximum likelihood estimation in the form of a numerical example as well, right? And then it is appropriate for probabilities that is that would completely fit in well for my case when I'm talking about logistic regression. So it would heavily penalizes the confidence wrong predictions. That is what I wanted. Then convex also has a single global minima for logistic regression and well-behaved gradients. It works well with the sigmoid activation, right? And the loss behavior is what? Loss increases exponentially as prediction diverges from the true level. And that is what I was wanting, right? The concept is same, so you don't have to the entire whenever you would talk about batch or SGD, I mean all those, so everything would be the same thing. I've already explained about it from batch to stochastic gradient descent. So I mean batch gradient over here, I mean it would uses all the training examples in update, obviously that we know. So so when you talk about in logistic regression, especially in classification problem, this the stochastic becomes more useful because you have to handle one class at a time because you want because ultimately, say suppose you have taken one sample and you have to reach towards a class, suppose X. So obviously, you would like to make changes. I would like to uh, uh, do the all the removal of the errors till it reaches to a class, correct class, then only would like to move to the second iteration or second example. So obviously the stochastic gradient behavior fits in quite well when it comes to these kind of classification problems in most of the cases, right? So as you understand and you know that in the batch gradient, all the training examples in one in each update where we used to do it, right? And the problem with the batch gradient is that it is slow for large data sets, right? Because when you talk about classification problems, you may not have a huge number of the classes, or you may not have huge number of samples where you want to do that, right? But again, depends, right? If it is huge, obviously you have to pay that particular price. So slow for large data sets, high memory requirements, and it is redundant computations when examples are similar, obviously. So when it comes to stochastic, so updates, as I've told you before also, we use one random sample at a time. They're much faster, and there are no memory requirements almost, right? So therefore, for classifications kind of problems, stochastic becomes more suitable kind of thing. So we have already talked about stochastic as such, that how it takes place in every iteration T. You would randomly select one example, you would compute the gradient, right? You would update the weights, right? And then the noise in the agility actually helps escape the local minimum and often leads to the better generalization. So we would take one example. I haven't covered the example, I could not. So maybe for the next iteration, I would fit in a very good example for stochastic gradient descent for classification approach so that you can go through it, right? So the gradient of the cross entropy loss for one example could be this, like this only, that you have uh, loss function defined, then you would actually calculate the error direction and the same structure that you did for the linear regression model. So I'll take up the example for the next iteration, right? Probably I've spoken a lot today. So what we'll do is we would um stop over here, and for the next iteration or for the next class, what I'll do is, because a lot of the concepts have been repeated now, so I would try to fit in some good examples before. Otherwise, the slide wise, I mean, this numerical example has been given already. Yes, we can take up this example if you want. Just wait. Yes, anyone wants to speak something?
Yeah. So, sir, one thing, right? Whatever the mathematical equations have
हाँ
been
दूसरा
written in the previous slides, right?
मैं
Uh,
थोड़ी देर में ढूंढते हैं ठीक है
Mhm.
hello.
Yes,
Yeah. So,
yes,
whatever
yes.
the mathematical equations have been written in the previous slides, right?
Mhm.
I mean, would we? How would we? It's quite tough to
So
write.
that's the reason.
Probably, yeah.
That's the reason. So that's the reason. That's the reason I told you that I have to need fit in a good example over here, the way I did it in the for linear regression model also, right? So I could not do that, although these are the actual slides. So you don't have to understand the point. You don't have to remember these things, right? You
Mhm.
just need to fit in a very simple weight update rule, and this is nothing but a weight update tool if you see very carefully, right?
Yeah,
This
yeah.
is the old weight. So you do not get bugged up with these things, right?
Mm,
So that's the reason I always prefer to take more examples in between, right?
mhm.
Mm, so I
So,
mean,
from an
you might.
exam perspective, right? Let's say we don't
So you
write
use your
any
own
of this.
terms.
Yeah.
No, you
Okay.
use your own terms, right? Why to use these typical looking examples or typical looking formulas, right?
Okay.
So if
Sure,
you
sir.
want to
Thank you.
use, so it's not an issue over there. So what I'll try to explain it with your thought process very clearly, because so I mean, this is a single neuron approach they have given. This is suppose a simple data set. So so obviously everyone knows it, like there are two ways to do it. One is you can do one iteration. I mean, you can express the entire x as a matrix. Otherwise you could have started doing one at a time, right? You could have taken one example at a time. So any approach is better. So normally when you do it in a programmatic wise, you prefer to use these kind of approach. So you have expressed x, y, and w in this form. So hyperparameters, we have given that. You have the initial weights defined, you have the sigmoid known, and then the loss function is defined, right? So you have to just remember what you need is just the understanding of it. You know y dash, what is y dash and what is y is the actual, and these are the predicted values, right? So you just need to remember this particular formula, nothing else. This is maximum likelihood function, right? So so the initial predictions, we would start with some of the W's, which we would took it to 0 and 0, right? So that is what, so what you get is Z value when you're going to compute Z values. So at 0, obviously, so it would result in a zero point 0.5. So that is the first, I would say, initial predictions, the first iteration that would be done, right? So you get when you have 0, 0, 0, 0 for all the inputs. So we had what? These are the inputs that we're talking about, right? So initial part, it would result in these values. These are the predictions, right? So randomly select the first example. So suppose I've selected this one. So what I'll do is I'll do a forward pass. This is the input, and the weights that we have taken was 0, 0, right? Isn't it? So obviously 0. And what we have obtained is zero point 0.5, right? Similarly, you would compute the error in that case. So you get the error of zero point 0.5 because 0 was the initially taken and zero point 0.5 you received it, right? Initially mean that was the output, isn't it? Output received. Why? Because that is what we did it, isn't it? This is how we, and when doing the first iteration, the first input 1 1. So this output was 0. So that's the reason it was 0, isn't it? That's the reason it was 0. And I took the first input. So first input 1 1 was having the output y is 0. So therefore, when you did this, you get zero point 0.5 as an outcome, and the actual value was 0. So therefore, zero point 0.5. Then you compute the gradients, right? Obviously, you would compute the gradients, right? So this is how, not a rocket science. You would update the weights, not again a rocket science. Same thing, right? So you have already taken this learning rate something. We would have we had already taken learning rate to be zero point 0.5. So do not get confused about all these things. It's a simple mathematics. It might look little difficult. Then you randomly select another input, for example. So what you got is the updated weights to be this one for a randomly taken input, this one. Then you again randomly chose another example. So suppose this one, 1, 3, and this was the output. So again, you do the same forward pass, right? I hope everyone now understand forward pass and everything. You applied this, you get this. After applying the sigmoid, you compute the error. Error was, the output was 1. So whatever you have to compute was on that basis. Then again, you compute the gradient, right? Then you compute the weights, right? So that is what you got, right? So after two SGD iterations, and we are doing SGDs, right? We're computing everything. So we got this, right? So we got this, what? Two, after the second iteration, I got this, isn't it? Similarly, example one, you could have done it. Example two, example three, example four, right? You could have applied this, isn't it? As you can see, similarly, for an example two, you could have done this. In example three, you could have done this. Example four. So example one and two, predictions move towards 0. Example 3, 4, the predictions are moving towards 1. So continue SGD for multiple epochs until the convergence concert. So I'll take a more better examples. This example they have given you, it's okay, but I would complete that picture of example. So what we'll take up is in the next session is a more complete example of this particular logistic regression through the new loss function, and then hopefully you would be able to understand little better, right? So for today, I'll end over here.
I have a
Little
question,
tired.
sir, on this
Yeah.
example
Yeah.
one and
Yeah.
two.
Yeah.
We are saying
Yeah.
predictions moving towards zero, but why we are saying that? I could not get that. Its output is still sigmoid output is
Example
0.7, 0.8.
true level 0, predictions moving towards 0. Um, just wait. I'm not confident about these slides, what they have written. So example 3 and 4, they say, uh, yeah, I'm also not convinced, yes. Not convinced, yes. Just wait, because they're not moving towards 0 for sure. Let me come up with my own example, right? I'm not little convinced with these example, what they have given. Absolutely, you're true. Because example 1 and 2 is also on higher side, and why they have said that it is predicting towards 0. I'll come up with my own example, right? These examples may not be completely true. Okay,
But they are
so
predicting Y bar only.
see, what obviously it's true. Either they have just said that the threshold that they have put in is in between this example 2 and 3, then it is true, right? But still, I need a more suitable thought process on it. So, out of these four predictions, they probably have put in a threshold in between, say, some example 2. So, all the values less than that would be heading towards 0. Mm, I didn't get much better understanding out of it. No. Mhm. I'll come up with my own better example, right? That would give you a better picture that how it is being doing. So I'm not very confident on the example they have used.
Um,
So we'll pick
sir,
up this in the next session because yeah. Yes, yes, please.
sir, sir, the threshold you mentioned that is also something we have to decide on our own, right? In the question.
That's what now. That's the only thing I could presume that they would have done in this case because that's the only thing that I could see. Otherwise, example 1 and 2, they say
So
that true
what is
label
the
is.
expected value of Y?
Just wait. No, no, no. Okay. Expected value of
Y bar.
an example
Y.
1 and 2. Just
Yes, because
that's
they're
what I'm
I
trying
think
to
they're
see.
moving to exam to the expected output.
Just wait. So in example 1, the output was what? Let us see. Example 1, the output was 0. Okay. And in example 2 also, just wait, let us see. Yeah. So in the first two cases was 0 and the next two cases were 1, 1. Okay. So they're explaining in that particular direction. So in the first two cases, they were supposed to be towards 0. Example 1 and 2. So example 1 and 2, true level was 0. So predictions moving towards 0. So these are lesser values they are trying to say as compared to the
Last one.
values of last two. So in that sense, it is true. Yeah. And example 3 and 4, they were supposed to be 1 and they are moving towards 1. So that is okay. In that sense, it is this example seems to be true. But anyway, I'll complete a picture. I'll give the complete picture of this particular example, and I'll come up with my own example that gives you a complete cycle because they haven't completed a cycle. And we need a complete cycle so that we can see. So in that sense, it is okay, obviously, because example 1 and 2, the labels were 0, and example 3 and 4 labels were 1. Yes. Okay.
So in
Anyway,
logistic regressions, we'll
yeah.
always be using sigmoid function.
Huh. We would always use a sigmoid function because see ultimately we sigmoid is producing value between 0 and 1. It's a continuous
Hmm.
value, right?
Hmm.
So since it is producing a continuous value, that is why that regression word is being attached. But ultimately we need to classify it now. So obviously the threshold value needs to be decided. So from where I have to separate the class boundary. So That theta has to be something, between the range of
Okay.
0 and 1. Hmm. Anyway, we'll end over here today, right? And we'll pick up from this. Not much is left. I think they have included confusion matrix and all those. If you want, I can cover these confusion metrics and all those right now. I mean, it is already. Let's pick up in the next session, right? It's not a much thought process which is left. We would be able to cover it. Okay, not a big issue. We are little, I mean, lagging in terms of 1.5. I mean, half lecture, not an issue. So we'll cover that. So okay for today, right? And let me just wait. Stop recording also. And in the next session, we would pick up